Hello, everyone. It's great to be part of the MLXN25 event. My name is Kamal Chaudhary. I'm a staff scientist at NIST. I would like to thank the organizer for organizing this event. Today, we're going to discuss about DiffractGPT, atomic structure determination from X-ray diffraction patterns using generative pre-trained transformer models. This project is a part of a bigger infrastructure called Jarvis, which is available at jarvis.nist.gov, joint automated repository for various integrated simulations. Before I go in details of the Diffract GPT, I would like to point out some details about inverse material design. So as a material scientist, we are familiar with the concept processing structure property performance relationship. Especially for atomistic material design, we have structure to property models. So suppose you know the atomic structure, then you can predict the properties using density functional theory or molecular dynamics and so on using well-studied, well-known physics models. Now, the idea of inverse material design is going property to structure. These properties could be scalar properties such as electronic band gap, formation energy, bulk modulus, thermal conductivity, and so on. It can be spectra or pattern or multiple value vector such as X-ray diffraction, or it can be images such as STM, STEM, and so on. And the idea is to go instead of structure to property, rather to go from property to structure. And it enables us to go beyond a funnel-like matching or screening-based material design. The idea is not new. One of the first papers I saw in inverse material design is by Alex Zunger in 2018 in Nature's Chemistry. And from there, we have developed several diffusion model for superconductor design, as well as forward and inverse material design, and also this diffract GPT work. I'd like to point out, although the idea is pretty fancy, there are several challenges. First of all, there are no physics-based models for inverse material design, so we have to rely on AI methods. And there are some certain methods such as genetic algorithm, Monte Carlo, cluster expansion, Bayesian optimization, but they are limited to handle complex material spaces. So for any inverse material or AI model development, we need well curated databases, benchmarking to know whether it works or not, and of course, selection of the AI models. So the models could be descriptor based models, graph neural network based model, generative pre-trained transformer model, and many type of model. And we'll be using GPT model for this work. So again, the idea of recent inverse material design is not something I started. There are several ongoing research efforts. For example, MIT had this paper on CDVAE, Crystal Diffusion Variation Autoencoder, MatterGen from Microsoft, Crystal LLM from Meta or Facebook. MIT recently also developed a framework or paper on crystal structure determination for Pyro diffraction patterns with diffusion model. And of course, we have our Diffract GPT work, which is complementary to these works. Now, let me talk about the Atom GPT first. So, at this point, we all are familiar with ChatGPT. It's one of the most remarkable advancement in the history of mankind, in my opinion. But if you go to the ChatGPT, and when I got my first hand on it in December 2022, uh, in addition to writing, for example, poem or songs or emails, I tried something like a prompt for material design. So here is a material such as magnesium boride, which is superconductor, and this is the bond length, this is the space group. Can you predict me the transition temperature? Or if I want a particular chemical composition and TC, can you generate me the crystal structure? So of course it did not work, at least at that time. So and also the models of ChatGPT are proprietary and they're closed and non-accessible to public. And if you have one prompt today and got a response, it might not be reproducible tomorrow. So which is problems for scientific research, because scientific research should be reproducible. So the idea of AtomGPT or motivation behind AtomGPT was to develop open access models that can work from multimodalities using transformer models for both forward and inverse material design. So the forward material design, you can see on the right hand side, as I said, we have the description of the material. So there are different ways to describe a material to a computer. Computers do not know physics or chemistry, or they understand only numbers or So we have to, for example, for GPT models, we can use the ChemNLP based describer to generate a description of any crystal structure. So for magnesium boride, it generated this description, and if I feed this model, it will predict me the TC, the transition temperature. Now the inverse material design is we provide an input. Here is the superconductor material. The chemical formula is magnesium boride. The TC we want is 32 or 39 Kelvin, and generate me the atomic structure determine description with lattice length, angle, coordinates, and atom types. So it will generate another string separated by new line character, the lattice length, angles, elemental types, and their coordinates. So this is the idea of text to text mapping using GPT models. So just a little bit more details about this, how it works. So the GPT model is based on this really famous article called Attention is All You Need. It has got 200,000 citation in last 8 years. And it's based on the mechanism called attention and basically how important each token or words are. So as I said, computers do not know physics, chemistry, they understand numbers. And if you have text, for example, hi, how are you? And the response is I'm fine. So if you want to give this information to computer, you have to convert this into a number, right? So what we could imagine is having a dictionary which is approximately suppose 200,000 or 50,000 words, and then we can find the index of those words: hi, comma, how, are, you, and question mark. And you can find where does it occur in the in a such as dictionary, right? And similarly for the response I am fine, we can find out which index these words occur. And then in this way, we can have this positional descriptor or positional values for each word. And we can have thousands of such documents, such as from Wikipedia, from New York Times, or some other um, resources from internet, and then we can tokenize, or that is convert words to numbers in terms of tokens, and establish the relationship between input and output. And now if you have a new question, for example, what's the capital of United States, the model will now convert this question or each word or character to corresponding token and try to predict the what will be the next token as a response. So that's how this basic idea, of course there are more details involved, but this is the basic idea how a GPT model works. Now, there are thousands and thousands of transformer models. So the one we use is Mistral AI model, which has 7 billion parameters. And I would like to point out a typical human brain has several hundreds of billion parameters. So these large language models are almost getting to the scale of number of neurons in the brain. So, of course, these models are pre-trained and available on Hugging Face. So we took this model, fine-tuned using some clever optimization technique, and shared the generated model on the Hugging Face again on KNC6 on my Hugging Face account, and it has been downloaded thousands of times. Many researchers are using it now. So a little bit more details about how it works. So the idea is parameter efficient fine tuning. So if we have the 7 billion parameters, and if you consider a floating number for each of them, 32 to 64 bytes, the data it will generate is just huge, and is very difficult to optimize such a huge parameter set. Even with our supercomputers or GPUs, it might take millions of dollars of compute power to optimize this kind of models from scratch. That's why what we do is we start with a low rank adaptation, automatic mixed precision, and some of the clever techniques to fine tune this model. Unfortunately, I'll not go details of this, but we found out these models can be used for both forward material design, promise energy, band gap, transition temperature, as well as inverse material design. For forward material design, it can beat, for example, for band gap and superconductor transition temperature, but it didn't beat for graph neural network for energy based prediction. But it did beat for diffusion based model, and the lower the value, the better. So in this way, we discovered new superconductors in our database and actually validated with DFT. Now the idea is diffraction. X-ray waves were discovered in 1895, and since then they have been really utilized in many instruments and experiments. And X-ray really play a crucial role in determining the atomic structure. However, if you take a crystal structure and try to have X-ray diffraction pattern in 1D, you lose lot of chemical and three-dimensional structure information in 1D pattern. And really, there is no physics-based model to go from a 1D spectra to directly to a crystal structure something like Schrodinger equation and so on. So when I started recently working on X-ray diffraction experimentally, I found this to be challenging and a great opportunity to apply GPT models. And this paper is now published in Journal of Physical Chemistry Letters and is considered as a highlight of that journal. So how does it work? Suppose you have X-ray diffraction pattern. This is my input spectra. I will take this from 0 to 90 degree 2 theta. And for 0 to 90 degree 2 theta, suppose we have a bin of zero point 0.1 or zero point 0.3 degree 2 theta. And then for each bin, we have the counts of the intensity. And then we will round it off to two digits, and then concatenate these numbers with a character such as new line character or comma, and that becomes a string. Now this is our input or x vector, or in the y we have our target, we have the crystal structure similar to the what we generated in the AtomGPT, such as lattice length, angles, and crystallographic coordinate element type. So you can see, for example, here's my chemical formula, here's the XRD, generate the lattice matrix element coordinates. And now you have different type of situation, whether you completely know the chemistry, you do not know chemistry at all, you know some idea of chemistry element list, and you know complete formula. So for these, you first tokenize the string of X-ray diffraction pattern, and then use three type of atomic structure depending on your criteria, and then further optimize with a unified force field such as align FF to get the structural candidates. Of course, you can also do pattern-based matching such as using Jarvis DFT. If you have a powered X-ray diffraction pattern, you can try it on the jarvis.nist.gov/jxrd for pattern-based matching. And for this DiffractGPT, we had to use some database for training our models. So we did not use any ICDD or experimental database because of the license or some other issues. So we tried our own Jarvis DFT database and simulated powder X-ray diffraction pattern, which is fascinating and very easy to generate. And these are some of the samples I personally measured. So these are EXP's experimental data, and you can see the theoretical data I developed. And you can see these are very close experiment, and they are over a diverse set of 80,000 materials with different crystal systems, space group, and so on. So they are very diverse. So we try to measure the performance of the model with formula, with element list, and with no formula. And we also had the model from gradient boosting resistance trees and convolutional neural network to predict the lattice parameters. Of course, they cannot predict the entire crystal structure, but we found that DiffractGPT model, especially with formula, can be have the lowest or highest accuracy. So here's again input for X-ray diffraction for silicon powder, and then when we give it to the model and it will generate a crystal structure, you can now predict its X-ray diffraction pattern. So we saw that the input X-ray diffraction has 6 peaks, but the DiffractGPT model has 7 peaks. But now we further optimize its aligned force field, you got 6 peaks back. And similarly, we generate for lanthanum boride, hafnium carbide, and so on. So we found that DiffractGPT for align FF could be used in principle for generating crystal structure, and not just for perfect materials, but also for defect material. Suppose you have an atomic structure and you displace an atom, and then you get the change in the intensity, but the peak value remains same. So we tried some silicon model for this, and we found that even though we did not train the model on defect materials like this, it can be used successfully for these materials. So these models are now publicly available on us.nis.gov/AtomGPT GitHub, and these are some of the notebooks you can try on your own on Google Colab. So in this talk, we learned about the NIST Jarvis infrastructure, different data modalities, AtomGPT, DiffractGPT, AlignFF, and in future, we'd like to extend this GPT for not just 1D but 2D diffractogram, neutron diffraction, and other experiments. So again, thank you for listening to this talk, and happy to answer any question. Feel free to email me in my email, or I'm also active in social media. And if you want to hear more talks like this, feel free to subscribe to my channel called Dr. Kamal Chaudhary on YouTube. Thank you.